Okay, now to something a little more concrete than the previous few lectures. So this is week 5, lecture 1 of the domain-specific languages of mathematics, and we will be talking about polynomials. So I'm starting from a quote from a maths textbook, where they define a polynomial in the following way. So a polynomial is a function p whose value at x is, and then there is an expression, where an to a0 are called the coefficients of the polynomial, and n greater than 0, and if n greater than 0, then an should not be 0. The number n, the degree of the highest power of x in the polynomial, is called the degree of the polynomial. And that they also claim that the degree of the zero polynomial is not defined. We'll get back to that later. Okay, it says the coefficients are constants. Well, that's good, because if they would be allowed to use x as a parameter, then every function would be a polynomial. They could just sort of do whatever they wanted. And this requirement that an is not equal to 0, that's about making sure that they don't have unnecessary zeros at the front. Just like when we write 125, we don't write 125. And similarly here, you can of course get the same function if you add more zeros in front of x to the power n plus 1, x to the power n plus 2, and so on. But they want to have the minimal, the shortest possible sequence of coefficients. Okay, now, as we usually do with these kinds of syntax or texts from a math book, we try to identify the types. So first of all, p, it says, is a function. So it doesn't really say from and to what. It could be natural numbers, real numbers, complex, and so on. Let's just assume here, and that's verified by the context of where this was found, that this is R to R. So it takes a real number and it delivers a real number. And then, of course, that means that the input, the first argument to p, is this real number. So that's a matching between the input parameter and the x. Okay, and then we have these different a coefficients. And if we ignore this side condition here, that it should be not 0 if nx greater than 0, then by multiplication being within the same set, we will assume that these are also real numbers. And this could be real number except for 0. So that maybe I should say a little or here. But let's, for simplicity, keep to the left. And well, all the coefficients here are just real numbers. So then you might wonder, what is a without an index? So the whole collection of coefficients. And well, they have choices here. I mean, it has a subscript, so there is some kind of method, something you can do with it to get a real number. And that means it could be a list or a vector, or it could be a function, and this is just function application. So let's use here as an example a function. Then you might wonder, what is the argument type to this function? Well, we see it being used with the numbers n down to 0. So at least those natural numbers should be in. So I guess we could have our homemade notation here, 0 ... n as a type, and then it should return a real number. And n, the degree of the exponents here, that's a natural number. So n and I actually, no, well, actually only n here. Okay, I mentioned we have different interpretations of the type of a. So we should note here also syntax-wise that with this interpretation we must perhaps add that ai means ai I mean function application of the function a to I. So that's sort of connected to this typing of it as a function. And an alternative is to say, well, let's say that a is a list of real numbers. And if we go with a list, then we also need to say that, well, actually ai means sort of index into position I in A. And oh, sorry, I I had scribbled too much here. This should be just normal list brackets, so the type of lists of real numbers. You might notice here that the type list of R is less specific than this type. So this type actually is precise about what we are allowed to index into. So here, if we say that A is just a list, then it's always the risk when we index into this list that we get an index out of bound. So maybe a third variant would be to say, well, A is of type vector of a vector of real numbers. So let's say a vector of length n plus 1 of real numbers. Okay, so there are different alternatives here. So that all these are sort of ors. So or this, or those over on the left there. So it's not all that important exactly which we choose, but we have to be consistent then afterwards. We will go with lists further on. Yeah, here I'd already filled in those types. Here I've collected the core, and I've even given the type of an index function, which also has this spurious extra bracket here. And defining the syntax. So now if we look at what we're doing here, the A can be seen as the syntax of a polynomial. So with syntax here, earlier we've had these data types, recursive most often, describing how you can build up an expression. And here it's not the same. Here we have a syntax with just a list of coefficients, so it's a little bit more sort of low-level syntax, but still we can see the list of coefficients as the core information of a polynomial, and the semantics is the actual function from real to real. So if we now just specify that we want to have a list as the type, then we can say, okay, let's evaluate this list of coefficients to a function according to this formula from the definition. And I said this is a bit of a low-level syntax, because we already have talked about in earlier lectures several times the data type funexp. And then we said that is a syntax, and we also know that we can evaluate that down to real to real. And with the funexp, with only multiplication, additions, constants, and x, we can actually always also evaluate it to this intermediate data type, which is the list of R. So this is a bit similar to, say, if we have a Java program as the top-level syntax, we have bytecode, which is basically a list of instructions, and then at the bottom level we have some machine code that runs the actual program. So we can compile it either all the way down to the machine code, or we can just go a little part of it to this list of coefficients of the polynomial. And this lecture we will not focus on the funexp part. We'll only look at the list part and the eval, but it's also a good exercise to implement ev, this evaluator from the top level syntax of funexp to the intermediate stage of these coefficients. Or I should also notice here it says syntax / semantics. So it just clarifies that, or I mean, shows at least that in some cases it's in the eye of the beholder. It's a choice if you see something as a syntax or semantics. So this first function ev, for that one, funexp is a syntax, and this list of coefficients is the semantics. For this eval, the list of coefficients is a syntax, and the function from R to R is the semantics. So we can have these towers of definitions where the role of being the input or output within a syntax or the semantics is interchanged. Okay, now let's go to some examples. If we fix to that we want to work with lists of coefficients as a syntax here, then first let's look on the right hand side at some examples. So we also want to fill in this definition, but let's look at the right hand side first. So let's start from below, from bottom. So first, if we want to represent the function that's a constant constant c, then we had in the definition 2 slides ago, the function should be this sum, but the sum could end with, well, it could have just an a0 in it. So in this case, we can fill in the list of just the constant 0. So the singleton list, the one element list. I should notice also in Haskell, when you write a one element list like that, it can also be written as C, and then the list constructor, and then followed by an empty list. So these things are actually equal. The upper expression is syntactic sugar for the lower expression. C followed by the empty list. Okay, then the next layer here, if we want to represent the identity function, the function which returns x, well, then there is no constant term. So if we want to have a list here, the first or the 0th argument should be 0. And then the coefficient in front of x is 1. So, I mean, we're using here that x, so x is equal to 1 times x to the power of 1 plus 0 times x to the power of 0. And then we write the elements in the opposite order because it's easier to work with lists starting at the constant term. Okay, and finally, moving up into complexity world here, we would like to represent the function that returns x minus 1 squared. Well, whatever the expression is there, we have to find what the coefficients of the square of the quadratic term is, what the coefficients of the linear term is, and what the constant term is. So let's make a little green arrow. Let's evaluate this part down here. So this is x squared minus 2x plus 1, which if you want to write it in the order of the list, it would be then 1 times x to the power of 0 plus, plus minus 2 times x to the power of 1 plus 1 times x to the power of 2. And from here, we can read off 1, minus 2, and 1 as the coefficients that should end up in our list representation. So I'm claiming here that the list 1, minus 2, and 1 is the syntax for the polynomial function x minus 1 squared. Okay, so I've written here as the top of the table that if this is a list AS, this should be eval L applied to AS. So I'm partially applying the evaluator I'm applying it to the list of coefficients, and I'm getting out a function. So that's why there is a lambda x here everywhere. And let's see if we can then fill in these cases. So the first case, the empty list, that's an easy case. So if we have no coefficients at all, then the function has to be 0. This is maybe not obvious, but it fits in very nicely with the algebraic laws here. So this is 0. And then to find out what we should write in the other case, so if the list is non-empty, if it has at least one component, which is actually the first component in this list, which means the constant term of the polynomial, and then some more list of coefficients afterwards. Then I will do an intermediate computation here, which indicates what we should write. So let's make the computation green, as we have underlined the functions as green. So I'm computing that we want to evaluate a polynomial of the shape ai times x to the power of I. This is from I equals 0 to n. So notice it's from 0 to n because we have a constant term with a 0th order term up to an nth order term. Okay, so I can extract the first term of this, which is just a0, and then restrict the sum to work from 1 to n. So I've done nothing else than taking out the first term, or rather I've taken out the 0th term here, the constant term, and notice that x to the power of 0 is 1. Okay, so the next step in the computation, then we identify the fact that all of the rest of the terms in this sum have at least one power of x in it. So x to the power of 1 is common to all of the rest. So we can extract that. So we can say it's still a0 plus, and then it's x times, and then still the sum from I equals 1 to n, and still ai, but now we have reduced the power of x. So it's x to the power of I minus 1. Okay. One more step. I want to change this form of the sum so it starts from 0 again. So we have an a0 plus x times a sum, and I'll just change the name of the index from I to j while doing this to avoid confusion. So j here is I minus 1. So the starting level is from 1 to 0, and the end must be n minus 1 then. Okay, so everywhere there was I before, I could say j plus 1 actually. So this is then a j plus 1 times x to the power of j. So I minus 1 was j. And now I should be able to notice that I'm using the indices one step away from the start. I'm never using a0 here, only the rest of the elements. So if we say that a here is our a0, that means that the other indices here are parts of as. So this is actually equal to a0 plus x times eval of as at x. Because the whole thing I was trying to write here, I forgot perhaps the first line, eval of a cons as at x. So evaluating a list which has a as the first component, and perhaps we should write it a0, and then as the rest, will, according to some algebraic simplifications, be equal to take the 0th component, add on to x times the result of a recursive call applied to x. So we can fill it in here, now in black, because we're back at the programming level. So this is a plus x times eval of as applied to x. And notice here I can underline eval of AS with green. So that is the function that eval returns, and that function is applied to x. So it's a little bit of a mix of math notation here and function notation, so we have to be a bit careful. So AS is the list, eval AS is the function, and I can apply it to x. Okay, so this evaluator that we've defined recursively here is a way of translating from a list of coefficients seen as the syntax of a polynomial to an actual real-to-real function. And with this evaluator, you can check that these equalities actually hold. Okay. Yeah, here I just had pre-written this to make sure that I fitted it on the slide. So let's move on. Now to an example, because we had some important word. Actually, maybe I should briefly go back there. In the original definition, it said that a polynomial is a function whose value at x is. So this does not say syntactically how p should be defined. It just should say when I apply p to an x, I should get the same result as if I would have written it in this way. But itself, it could have a definition containing all kinds of other functions, as long as they behave like a polynomial. Let's see, I think we were at this slide. So I want to take this example of what is called Chebyshev polynomials, because they definitely do not look like polynomials first, and then you can actually prove that they are. And it's also an exercise in using the notation for homomorphisms. So this is a bit of an unusual case. So now we're not talking about homomorphisms in the sense of translating an eval function from a syntax to a semantics. It's really two different semantics here. So we have cosine, so the trigonometric function cosine, as the homomorphism. And the homomorphism is from the function that multiplies its angle by n and another function tn. And the claim here is that tn is a polynomial function of degree n for every n, where n is a natural number. So in some sense, multiplying by n is transmitted by cosine to some more complicated function. So this is a sort of very simple function on the angles, and here we got a polynomial, or at least some function which we will prove is a polynomial, acting on the resulting cosine. Okay, so let's check the types as usual. So cosine here, I will give it type r plus to I, where I defined r plus to be the non-negative real numbers, and I to be the interval, I for interval, between -1 and +1. Okay, so we know that cosine will return a value between -1 and +1. So that's why this is a reasonable typing of it. And then when we're talking about homomorphisms, we know that the homomorphism, usually called age, but here cosine, should translate from sort of one world to the other, and the operators it translates between should live purely within one or the other. So if we remind ourselves what the typing is here, we should be in the A world, which is here r plus with the first operator, and we should be in the B world, the I, with the other operator. Okay, so now we have the typing in place, and let's try to see what this entails in the three simplest possible cases. So first, I write out this abbreviated form. So H1 is defined so that it expands to this. So it has an index 1, meaning a quantification of a 1 argument, and that in this case are angles V of this type R+. So for every angle V, if we first multiply it by n, and then take the cosine, it should be the same as applying a certain function to the result of applying cosine to the angle before multiplication. So it's not obvious if this will work, but we can prove it works. There is an exercise to do it as well, but we can try it at least for a few simple cases. So the simplest possible case clearly is n equals 0. So if n is 0, then n times v here is always 0. So then the left-hand side of this equality is cosine of 0, which is 1. Maybe I should add that. So this is equal to 1, just a constant 1. It's good at least that it stays within this range, -1 to +1. And then we want to find a function t0 such that when applied to cosine of v for any angle v, we should get 1. Well, that's a rather easy application. So t0 can just throw away x, so the cosine of v, and return 1. So let's do that. And then we have to think, okay, is this a polynomial? Well, constant functions are polynomials of degree 0. So yes, this first case works. t0 is a polynomial of degree 0. Okay, the second easiest case is when we take n equals 1. And then the cosine of n times v, well, that's just the cosine of v. And here we want to find a function t1 such that when given cosine of v as an argument should return the cosine of v. Well, that's simple as well. That's just the identity function. Okay, so the identity function is t1, and we can check, does it have degree n? Yes, it has degree 1, because n is here 1. It also stays within this interval. If you give it -1, it will return -1. If you give it 1, it will be 1. So it matches the type I to I here. Well, also this one matched. If you give it any value, it will be 1, which is within the interval. Okay, let's move to a little more interesting case. So I repeated some of the code, including the expanded form, and now we will have to look at the case where n is equal to 2. So then the left-hand side is the cosine of twice the angle v. And if you look up your trigonometry tables, it will say actually one way of writing this as twice cosine squared minus 1. And then we'll have to find, is there a function tv which transforms cosine of v to this expression? And as you can see, we're in luck again, because this just takes cosine of v, squares it, multiplies by 2 and subtracts 1. So this is just 2 times x squared minus 1. And then we can again check, well, this is a polynomial function of degree 2, where n was 2, so it seems to work. And we can, if we sketch it, we can see that it has this shape. So here is -1 to 1 is the interval I it should start from. And if we take the smallest value as input, -1, we get 1 when we square it, times 2, that's 2, minus 1 is 1. So that's the first point. If we take 0, we end up at -1. And if we take 1, we end up at +1 again. So if we sketch it, you get this shape, and you can see it's still fits. It comes from the interval I, and it returns the interval I. And actually it precisely fits. I mean, it attains the top value and the bottom value in this interval. And actually, if you look more generally at this, if we define the angle v to be the inverse of cosine, so arc cosine, which is well defined on this interval I. So this function from r plus to I, if you invert it, you come from I, and then you get back to r plus. Then we can actually write any of these functions as Tn of x is the cosine of n times the arc cosine of x. So this will satisfy this law sort of trivially, because it will take cosine of v in, and then we do arc cosine of it, we'll get v back, and then we'll say n times that v. So the left-hand side and the right-hand side are equal. So this definition clearly satisfies the homomorphism condition. What is not at all clear from this definition of the function is that it is a polynomial. And for that you actually need a proof. And I think the easiest proof is by induction and using some trigonometric laws. And we will not do that here, because we've reached the little marker that indicates that we should now make a break in the lecture before we move on. But to sum up here, the last few slides I've talked about a special class of polynomials, the Chebyshev polynomials, Tn, which have the property that they can be defined by an expression which looks eminently trigonometric, and it doesn't have any sign of being a polynomial. And still, the actual function Tn for every integer, for every natural number n, is actually a polynomial. So that's one of the interesting examples showing that the definition, as we referred to, talking about a function that behaves like a polynomial, is important here. It's not written as the sum of x plus x squared or something like that. It's written in a completely different way, but its value behaves as if it were a polynomial. So therefore it is a polynomial function. Okay, that's all for this part.